of thousands or even millions of Kelvin, far hotter than models of simple photoionization could account for. The discrepancy became known informally as the IgM temperature problem, and it has occupied cosmologists since the 1990s. Something is pumping enormous quantities of heat into the void between galaxies, and for a long time, nobody could convincingly identify the source. The leading candidate today is a process called helium reionization. Helium, unlike hydrogen, requires much more energetic radiation to strip its second electron, and the objects capable of producing that radiation are quasars. A 2019 study using the cosmic origin spectrograph aboard the Hubble Space Telescope provided strong supporting evidence that a burst of helium reionization driven by quasar activity between about 3 and 4 billion years after the Big Bang heated the IgM substantially. A separate mechanism, blazar heating, was proposed by Avery Broderick and colleagues in 2012, suggesting that the high-energy gamma-ray jets from active galactic nuclei deposit heat directly into the surrounding intergalactic gas. Neither mechanism alone fully resolves the temperature budget. The two processes together bring models closer to observations, but significant uncertainties remain, particularly in the densest filament regions where the temperature excess is most pronounced. The intergalactic medium is also not uniform. It has a complex thermal structure shaped by the history of cosmic reionization, galactic feedback, and processes that simulations are only beginning to reproduce with reasonable accuracy. The void between galaxies is not cold and dead as it should be. Something has been heating it for billions of years, working through mechanisms we have identified but not yet fully understood, maintaining temperatures in regions of near-perfect emptiness that rival the outer layers of a star. The universe, it seems, does not allow its empty spaces to simply go cold. Number 7. Fast radio bursts. On July 24, 2001, a burst of radio energy crossed billions of light-years of intergalactic space and was captured by the Parkes Radio Telescope in New South Wales, Australia. Nobody noticed for 6 years. It was astronomer Duncan Lorimer who found it in 2007, sifting through archival data with his student David Narkovich. And when he saw the signal's dispersion, the way its different frequencies had been spread out by the electrons it had passed through on its journey, he realized it had come from far outside the Milky Way. In a few milliseconds, whatever produced this burst had released more energy than the sun emits in days. Fast radio bursts, FRBs, were initially so extraordinary that significant portions of the astronomical community suspected they were interference, some earthly contaminant masquerading as a cosmic signal. The Parkes telescope had been fooled before. It took years of additional detections and the eventual real-time capture of bursts by multiple independent observatories to settle the debate. They were real, they were extragalactic, and they were happening constantly. The Chime Radio Telescope in British Columbia, Canada, began operations in 2018 and rapidly transformed the field, detecting hundreds of FRBs and revealing a phenomenon far more diverse and complex than anyone had anticipated. Some bursts repeat, firing again hours or days or months later. Others have been detected only once. Some repeat with eerie regularity, like FRB 180916, which fires in a 16.35-day cycle, suggesting an orbital or rotational clock of some kind. The source distances range from hundreds of millions to billions of light-years, scattering them across a vast span of cosmic time. In 2020, a breakthrough came from inside our own galaxy. An FRB was detected originating from SGR 1935 plus 2154, a magnetar, a type of neutron star with an extraordinarily powerful magnetic field, located about 30,000 light-years away. This was the first time a source was directly identified, and it strongly supported magnetars as at least one type of FRB progenitor. But magnetars cannot easily explain the full diversity of observed bursts, particularly those with precise periodic behavior, and the full taxonomy of what produces these events remains an open question. Every day, by theoretical extrapolation, hundreds of thousands of fast radio bursts cross the observable universe in all directions. We have cataloged only a tiny fraction of them, and even that fraction contains mysteries that our best models cannot fully explain. The universe has been producing these millisecond screams of energy since long before Earth existed, and we have only just learned to listen. Number 6. The supervoids. In 2004, astronomers analyzing data from NASA's WMAP satellite, which had produced the most detailed map yet of the cosmic microwave background, noticed something wrong with a patch of sky in the southern constellation Eridanus. The CMB, the ancient afterglow of the Big Bang, should be very nearly uniform across the sky with only tiny temperature fluctuations of a few millionths of a degree. In this particular region, however, the temperature was measurably and stubbornly lower than it should be, by approximately 70 microkelvin. They called it the cold spot, and it has not been explained satisfactorily since. The cosmic microwave background is the oldest light in the universe, emitted roughly 380,000 years after the Big Bang, and carrying encoded in its temperature variations the seeds of all the structure that followed. Anomalies in it are taken seriously, because this light has been traveling toward us for nearly 13.8 billion years, and anything that disturbed it left a mark that persists. A cold spot of this magnitude and angular size sat at the edge of what standard cosmological models predicted could exist by chance. In 2015, a team led by Istvan Saputty at the University of Hawaii identified a supervoid aligned with the cold spot, a region of space approximately 1.8 billion light-years across, containing roughly 20% fewer galaxies than a typical region of its size. Published in monthly notices of the Royal Astronomical Society, this was the largest supervoid ever identified, and it offered a potential explanation. Photons of light lose energy as they travel through large empty regions, a phenomenon called the integrated Sachs-Wolf effect, and this energy loss would show up as a cold patch in the CMB. The numbers, however, did not fully add up. The supervoid accounts for some of the temperature deficit, but not all of it. The cold spot is colder than the void alone can explain. The remaining discrepancy has attracted increasingly exotic proposals. Some researchers have suggested the cold spot might be a gravitational imprint left by a collision between our universe and an adjacent bubble universe during the inflationary epoch, a bruise in the fabric of the CMB left by contact with something outside our observable cosmos. This hypothesis is considered fringe by most cosmologists, but it has not been formally ruled out, and the Planck satellites data confirm that the cold spot's anomaly persists even in the most sophisticated analysis. A billion light-year hole in the universe, in a direction where the oldest light in existence runs measurably cold, and our best models still cannot fully account for the temperature of that silence. Whatever explanation eventually emerges will need to be something genuinely new, because everything we currently have falls short. Number 5. Dark matter and the invisible scaffolding. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford sat with data from the Kitt Peak National Observatory in Arizona and measured how fast stars were orbiting the centers of galaxies. According to Newtonian gravity and everything known about the distribution of mass in those galaxies, stars at the outer edges should be moving more slowly than stars closer to the center, just as the outer planets of our solar system orbit the sun more slowly than the inner ones. They were not. Stars at the edges were moving just as fast as stars near the core, sometimes faster. The galaxies should have been tearing themselves apart, and they were not, because something invisible was holding them together. That invisible something was not a new idea by the 1970s. Swiss astronomer Fritz Zwicky had proposed in 1933 that galaxy clusters contained far more mass than their visible stars could account for. But Rubin and Ford's rotation curves turned the hypothesis into a crisis. Galaxy after galaxy showed the same pattern. The mass that gravity required to explain the motion was simply not there in any form that emitted or reflected light. Something dark, something enormous, something unknown was doing the work. Today, dark matter is estimated to make up approximately 27% of the total energy content of the universe, compared to just 5% for all ordinary matter, every star, planet, gas cloud, and atom that has ever been observed. In the intergalactic context, dark matter forms the scaffolding of the cosmic web itself, the invisible filaments along which galaxies cluster, the unseen halos that surround every galaxy, the gravitational backbone of all large-scale structure. The most direct evidence came in 2006 from observations of the Bullet Cluster, two galaxy clusters that had collided, published by Douglas Clow and colleagues. Gravitational lensing maps showed the mass, and therefore the dark matter, had separated from the hot gas during the collision, drifting ahead of it like a ghost stepping through a wall. Despite 5 decades of increasingly sophisticated searching, dark matter has never been directly detected. The Xenon 1T experiment in the Gran Sasso laboratory in Italy, one of the most sensitive detectors ever built, found nothing. The Large Hadron Collider at CERN has found no particle that fits the required profile. Proposals for what dark matter might be, WIMPs, axions, sterile neutrinos, primordial black holes, continue to multiply and continue to go unconfirmed. Every candidate has survived only because it has not been decisively ruled out, not because it has been found. The architecture of the entire universe, every filament, every galaxy cluster, every structure that has ever formed, is built on a foundation of something we cannot see, cannot touch, and cannot detect with any instrument yet devised. It outnumbers ordinary matter by more than 5 to 1. It is everywhere, and after 50 years of searching, we do not know what it is. Number 4. Quasars, the most violent objects in the universe. In 1960, astronomer Martin Schmidt was working at the Palomar Observatory in California, studying the optical counterpart of a radio source designated 3C